We start with our afternoon session. The first speaker is Gianluca Mastrantonio, Politecnico di Torino. He will talk about Bayesian size and shape regression modeling. Prego, Gianluca.
Thank you. So today I'm presenting to you a joint work with Giovanna Gionasino, which is a professor at Rome, and Antonio Di Nola, which is now a PhD student in Switzerland, I think. Is a PhD students, and the results I'm presenting here are based on the master thesis of Antonio. The general setting is the statistic analysis of shape. So how do we take a shape of an object, how we take data from an object, how we extract the shape of an object, and how to define a model shape object, and also for the size. So everyone, basically everyone have an idea of what a shape of an object is, but we need something that is more rule in mathematics, and also a way to define and gather data from shape of an object. So to understand what the data are, I can introduce the concept of landmark. So the idea is to, let's suppose we have different object, like in this case is a scale of I think, and we can define this landmark. Landmark are points that are relevant to this object, and we can recognize these points over different scales. So for example, here we have this point, I don't know here, which is close to the nose. So we have this landmark, and we can record the coordinate of this landmark for different scale. Or we have different here, like this part here or here. It's something that has some kind of meanings for the people that have recorded this data. The landmark are quite useful, but it's not always possible to have landmark like this. For example, classical example is the handwriting. So let's suppose we want to recognize the handwriting. This is a tree. So if you want a landmark for this tree, this number here, of course you can take this part here, the lower part, landmark number 1. We know that this is a tree, so we can take the 7, so the first arc. We can take the 13 landmark, but then there is no other type of landmark that can be shared across different samples. What generally can be done is to use some mathematical definition. For example, we can take this landmark here, landmark 4 and 10, which are the point at maximum curvature. And here between landmark 7 and landmark 10, we took this other two landmarks, which are just equally, the distance between landmark 7 and 8 is just the same. Actually, it was not true. I made a mistake. So we can basically define some kind of definition, we can find some definition to use this landmark. Now, when we have an object like this and we want to extract the shape of an object, there are different ways to extract the shapes. There are different type of information that we want to retain from the shape of an object, or other information that we want to discover. So let's suppose again we have this coordinate of this tree, and we can apply different transformation, and we can decide if the transformation is important. So if we apply this transformation, we get a different data or not. For example, here we have this original tree. The coordinate goes from -40 to -10 here on the y-axis. Here it's from 10 to 40, and we can translate the tree. This is a new set of coordinates, but if we are interested in the shape, this should be the same object. Just a translation, the shape of the object of the tree is basically the same. Again, we can think that we can take the tree and rotate the tree. Again, maybe we are not interested in the rotation of an object. Or maybe we are, because if we take a tree or we take a tree but rotated, maybe it is a different object, a different shape for us. It depends on the application. Other type of transformation is the rescaling. So we take the tree and we shrink it. And again, if we want to work with the shape of an object, probably rescaling is something that we don't care very much. But if you're working with the size of an object, like the size and shape of an object, we shouldn't allow rescaling. So the rescale of an object is a different object for us. Okay? While if you're interested in the shape of an object, rescaling is something that we are not interested in. Another possible transformation is reflection. This looks like a rotation, but it's not, because here you have the first landmark, now it's here the landmark, and now it's here. This is a reflection. For the tree, maybe we can allow a reflection, but there are other objects that if you reflect with respect to some axis, it's a different object. Okay? Based on what we allow or what we want the inference to be unaffected to, we can define different types of data. In this project, in this presentation, working with size and shape data. So data that are invariant under translation, so we can move the object, and the object can still the same size and shape, and we can rotate the object. Okay, but we do not allow reflection and rescale. Okay, if we take the size and shape data and we allow reflection, we take reflection size and shape data. If we allow rescaling, we obtain reflection size data, or again size data if we allow only translation relation scaling. Now we need something a little more technical. Okay, so let's suppose we have this matrix which has k+1 row and p column, and this represents an object. Each row is a landmark. So landmark 1 is the first row. In the landmark 1, if you're working with an object, a two-dimensional object, p is equal to, and so the first row represents the two coordinates. So p gen is 2 or 3. Okay, and the idea is what's the shape and size of this object. Okay, the idea is to first define this equivalent class. So all the object that if we take x above, and we rotate x with this rotation matrix, so a matrix that belongs to a special orthogonal group, and we translate, we move with this vector tau. The new object, this new object here, has again the same shape, size and shape of the original object. So all the objects that can be constructed with this equivalent class have the same size and shape. This helps us in defining what size and shape is. So again, is the definition, geometric information about x that is invariant of the equation notation. But we still need the data. So we have observed the landmark, k+1 landmark, and we need to extract the data, the size and shape data, and we need a model. So what we did is to take the original data and we applied two transformations. The first one, remove location. The second one, remove location. Okay. The idea is we define these two transformations. Then if we take the original data and we rotate the original data and we translate the original data, we apply the same transformation, we must obtain the same data because the size and shape should be the same. So location is removed with this complex matrix, the Elmer matrix. Actually, a statistician should know this matrix.
Madonna Cristo. Che morto di sonno, Madonna, che morto di sonno, che morto di sonno.
Okay. So it's the matrix that you use to demonstrate that the sample variance and the sample mean of a normal distributions are independent. Actually, it's not the matrix because there is a row missing. The first row is missing this Elmer-Tizer. This is an Elmer submatrix. It's the first row is missing. So we multiply the original data by this matrix, and we obtain the new data, the Elmer-Tizer configuration, which now has dimension k, row and p column. So we are missing one row, one observation. Because basically we're moving locations, so we are moving a degree of freedom. So we have to lose. So the idea is you multiply this value with the Elmer-Tizer matrix, and you lose a landmark, and you obtain the data that is variant and the translation because you cannot basically move the data anymore. Okay, I'll explain later what that means. Another possible way, something similar, is basically the same thing. Just take the first landmark and assume that this landmark is equal to coordinate 0, 0. You are fixing the object in space. So okay, and this is another of this type of transformation, but there is a one-to-one relation between this transformation and this. Yeah, transformation is pretty easy. We have the lattice configuration. We have the singular value decomposition. The singular value decomposition is three metrics. The third one is a rotation matrix. So we can discard the rotation matrix. And U lambda, the multiplication between these two, are actually the size and shape of the original data. To demonstrate that this is true, we can take the original data, we can translate the original data with this vector tau, so we are moving in space. We can rotate the original data with this matrix R, rotation matrix. And if we apply the transformation, I'll show you that we still obtain the same Y. This is easily proven because the a vector of 1 that multiplied times matrix is a vector of 0. So when you apply the times transformation to the translated matrix, you obtain basically H that multiply the original matrix for the rotation. And when you again apply the single value decomposition, these rotations here just multiply the original rotation. Again, you extract just the first two matrices, and you obtain the same result. So this is our size and shape. Now, we have defined the data. So, okay, we have our data. So we have X, we have our data Y, and now we want to model the relation between the size and shape and some covariance. Okay? Well, that's really hard because how do you define a link between the size and shape object and the original covariance? In Bayesian statistics, actually, even if I go to statistics, but in Bayesian statistics, quite easy to do it. Sometimes when you cannot do something in the original space, you add some latent variable. And maybe in the space where there is this latent variables, the relation between the two original quantities are easier. And we are kind of lucky here, because it's true that here we have first have the data, we remove location, and we don't care about location. But the important thing is we remove rotation. But we can actually reintroduce rotation, because once we introduce rotation, this is just data that lives on a p-dimensional space. But we shouldn't reintroduce the original rotation. The original rotation is something that we don't care about. We introduce a random rotation, something that is not connected to the original data. What we say is that the data, the size and shape, multiply a rotation, is normally distributed. This is kind of like before, but we can rewrite it this distribution more easily. We can say that this Y star L is column L of the matrix. It is the multiplication between the size and shape and the rotation. So we take the size and shape, we multiply multiplication, we take one column, and we say that this column is normally distributed with some covariance sigma. And this is basically a regression, where the regressors depends on the column. So each column has a different set of regressors. Now,
each column is originally related to a landmark, right?
What?
Each column is originally
related to one coordinate of each landmark. Yes. Yes. So we are seeing that the coordinates are independent. All the set of first coordinates are independent. We have to do this because the dependence between the coordinates is actually not identifiable. Because we are removing rotation, so we can rotate it and actually find the specific rotation where the coordinates are independent. So there is no way that we can identify the dependence between the coordinates. So now the problem is we are introducing this rotation matrix R, but the rotation matrix are random variable. So we have to find the distribution of this random variable. and the distribution should be a distribution that makes the original data invariant and the rotation. So what I mean with that, if we assume that the original data is normal and we remove the rotations, we obtain the data, the size and shape that is from this distribution called offset normal. What's more important is distribution with the rotation matrix. The distribution with the rotation matrix turns out to be a matrix Fisher distribution. But the important aspect of the distribution that a priori, when we assume the normal, we try to find the distribution of the rotation matrix. This is uniform in the space of the rotation matrix. So we are not adding information. Any rotation has the same exact probability because we are working with size and shape. So rotation, there is not a particular rotation that is more important than another one. So the distribution is from a uniform distribution. Now we have to variation, so we have to estimate the model. So basically, we have to define a prior distribution for the regressors and sigma. But if we look here at the data, I know that Y star is composed of the size and shape and the rotation, but from the point of view of beta and sigma, they're just mean and covariance of a normal distribution. So we can use the standard prior. Beta is multivariate normal, sigma is inverse Wishart, and when we try to implement the MCMC, they don't care about the rotation, the size and shape. They're just part of the normal distribution. So the full condition of beta and sigma are just the same full condition that you would have in a regressive mode. So this is just normal and so standard full condition. The vector regression is still normal, Y is still inverse Wishart. We have also to find the full condition of the rotation matrix, one for each observation, and this must be again matrix spatially distributed with different parameters. The matrix spatial distribution is hard sometimes to deal with, but we are lucky because when P is equal to, so two-dimensional data, the matrix spatial is a von Mises distribution, which is a standard distribution. So we can sample using directly from the full condition. When P is equal to 3, we can't really sample from the matrix spatial distribution, or we can express the rotation matrix with the Euler angles. And there are some tricks so that we can basically sample from the matrix spatial distribution with metropolis. When P is greater than 3, I think it's not possible to obtain direct sample from the spatial data if you're working with data in 2 dimensions. Yeah, but if you have more abstract objects, you can have object in strange image. Again, when we work with size and shape, there are a lot of problems because the idea is that there are transformations, scaling, rotation that shouldn't matter. But from a modeling point of view, this means that most of the time the parameters are not identifiable because I can take the mean of the normal distribution, I can rotate the mean, and I obtain the same exact model because rotation doesn't matter. So we are generally, in this model, it's actually quite easy. We what I did is just try to compute the ratio between the density of the original data with some vector mean covariance and the original data when I rotate the mean. And it can be shown that this density, this ratio is equal to 1, this means that you can identify the parameter. So you have to fix some parameter, and the basic idea is if you have an intercept in your model, you say that one of the intercept is always positive and one is always 0. The regressors associated to the intercept is always 0. So you cannot anymore rotate because if you rotate something, the intercept will change the value. So it's 0 when you rotate the model. I mean, will be different from 0, so you cannot rotate anymore. And the fact that you assume that one intercept is always positive, you cannot anymore reflect it because from positive will become negative. So you have to apply some transformation just to do that. Almost done. I don't have real data. I just have some simulation because the idea is to see if this approach worked. So let's simulate from the data. Let's simulate from the normal. Let's look at rotation. It takes size and shape. We apply the transformation, and let's see if we are able to estimate the data. So different setting. We have landmark. To set landmark 10, 20 landmark. 20 or 100 observations. Lambda is a factor that multiplies a diagonal coordinates matrix. And we try with two-dimensional P equal to a three-dimensional. What is important here is even when you have something like 20 observations and you have 10 landmarks and P is equal to, that is the smallest set of observation, you still will have 59 regressors and 55 values to estimate for the covariance matrix. So there are many parameters. And in the highest setting with 20 landmark P equals 3, with just 3 regressors, you will have 400 parameter estimates. So that's really intensive. But just some table to show you here. I show you the this is the length of the credible interval. And this is how many parameters are well estimated. Because for each setting, estimated 100 data set. Here I count how many times the real values is inside the associated credible interval. As you can see, the credible interval is a 95 credible interval. More or less, we get 95. The length of the credible interval, of course, increases with lambda, which is the variability. If you increase the variability, lambda, you increase the length of the credible interval, increases and decreases with the n, with the sample size. The observation you have smaller is the credible interval. And when you increase the dimension, so this goes for the two-dimensional data, when you increase the dimension, everything gets a little bit trickier. So the intervals are again something to see remark. The idea is the model is actually easy to implement when you understand the full condition of the position matrix. It's easy to interpret. I put relatively because you have to take into account that everything you say should be true, but with regards to the rotation. So when you try to interpret data, mistakes will occur. There is actually a Julia package, out of this Julia package, if you want to try, but it's in something shape. And we are further developments because the basic idea is we don't like the idea that we are using a generic covariance matrix. If this object represents shapes that are point of the shapes that are connected. So the connection should depends on maybe how close they are or if they are important to each other. So we want to try something like random field type dependence or network.
Thank you, Gianluca. So let us see if there are questions from the public remote session. If anybody has some question, any question? Or then hear from people in the room, Sophie and then Mauro.
Thanks so much. I have two questions regarding the extension to random field.
What, sorry?
You mentioned extension to random field.
Yes.
To work on random field.
Yes.
So what do you mean by using random field in this shape point of view?
Well, when you're working in the spatial set, you can define a car model when you have the points that are close, like say, you have a classic example, you have a state, where the mortality rate, the number of people that died from some disease, and this number depends on the neighbors, just on the neighbors. And you can construct a network with observations, so the distribution of one state depends on the neighbors. We want to do something like that, like where the coordinates of one landmark depends on what happened to the landmark close to it. If this is an object, if this landmark here should move depending on this one.
You said
maybe also on this one here.
You said they were independent.
No, they are dependent. The coordinates, the first coordinate of this one is independent from the second coordinate of this one. But the first coordinate of this point here, the first coordinate of this point here, the first coordinate of this point here, these are dependent. So they should. Maybe this point here should be independent from this, but not from this two.
Using network matrices to calculate.
Yeah, yes. So because when you work with car model, you always have or positive dependence or negative dependence. But here it's a mix of the two, because maybe between one point there is a positive, between another two points there is a negative, because if you're always positive, you just moving the object. If you're always negative, you're taking the object down. So that's
What's more suggestion? You talk about the dimension of the landmark that is a problem. Okay. And perhaps one solution would be to take your shape of landmark at one object in a space of function, and this would be only one data set. And there are in functional data analysis.
that's
people where
this
so
is, yeah,
this
this is also, we are trying
analysis
also
as
as well.
yeah.
But this is actually, this is
Exactly.
a really, just start working. So yeah.
I thought I thought you would go immediately for mu equals for a non-informative prior in this case, because you have all this rotation thing.
Yeah, you can just use a general structure, yeah, of course. Just using prior with some variance, but basically I'm setting m equal to 0 and u equal to, I don't know, something like 10,000 for a diagonal matrix, just generic structure.
And historically, how is this related to all the work that has been done in engineering and recognition, image recognition?
Yeah, there's not been using a lot. But what I found really strange that there is a lot of statistical analysis of shape from the descriptive point of view. When you start to think about modeling, there is just this and other two works. There are just three works of modeling.
And what does descriptive mean?
I was working on this in functional data. I was surprised that
There
in
is
the
not
statistical
enough.
point
Yeah,
of
exactly.
view,
This model is quite easy.
yeah, you have both on morphology, etc.
Yeah,
but using
but there is not.
Yeah, because what you did was geometry. Up
Yeah, it is
until
geometry.
slide 14 was computational geometry.
Yes, computational geometry. Yes, exactly. But the stuff, the margin is the one that.
Market in this
Yes, of course.
base.
No, the book, the standard book for the standards of shapes from margin.
It's computational geometry.
Basically, yes.
Mostly.
Yeah, there is a lot of computational geometry. Yes. But you're
This
working
is
with
what the engineers use for.
I don't know.
The Chinese use image reconstruction for security all the
I think it's
time, right?
something like
They do
this,
that.
I don't know.
Do they do that?
Yeah.
They use this.
yeah, but here you are not really interested to construct. You're going to use all the shape.
Yeah, well,
But
yes, but you,
what is done in in image analysis using supervised or non-supervised devices will also be applied to this. Yeah. The fact that is the shape, there is some dependency, spatial dependency to take into account.
yeah, that's what I want to do. Actually, I work with special data, so yes, that's what I want to do. What's special?
Okay, thanks a lot. Then thanks again,
Thank you.
Gianluca.